Pizza is a very important part of modern day society. With the continual advance of technology, it is important that pizza delivery is able to keep up. Enter drone delivery. For the first time, pizza can be flown to a customer's door. The only problem? Drones aren't exactly pizza friendly. For one, they can't instinctively avoid obstacles like a human delivery driver can. Drones can react, sure, but the new path may be jerky, getting cheese and sauce all over the cardboard delivery box. Drones may also release a pizza from what is seen to be an acceptable height, but which may be too high, leading to a meeting with the ground that results in mangled pizza inside a damaged cardboard box. In the air, a drone can get knocked around by the wind, or even birds, neither of which is a good friend for pizza. Luckily, there's a solution to all these problems: control system engineering. With some attention to factors like steady state error, settling time, and disturbance rejection, the pizza can be safer on its delivery flight. The drone we picked to use is a DJI Phantom 4. This is a very commonly modified drone in the original research for a drone project like this. Most thermal imaging cameras that are on drones are developed on one of these before moved to a different platform. We think that this platform is good enough because it can produce 800 grams of thrust per motor. But it does max out at around 1600 grams, just because the motors are spinning opposite directions. The drone weighs 1.375 kilograms and produces 800 grams of thrust per motor. With the drone and the payload, that gives it a payload of a little over 1.6 kilograms.
For our purposes, we will only consider the drone's movement in the vertical direction, hereon referred to as height, or h. The drone can be modeled as a simple mechanical system, a mass acting under the upward force of the drone's motors and the downward force of gravity, and the damper, which represents air resistance as the drone moves. The sum of forces acting on the mass is equal to the mass times its acceleration, which is the second derivative of its height, plus the damping constant multiplied by the first derivative of the drone height. We can convert this equation into the frequency domain using Laplace transforms, and assuming the drone is at rest, this equation simplifies down. From here, we define our transfer function, our output, which is the height of the drone, over the input, the force acting on the drone. The final transfer function comes out to be 1 over ms squared plus bs, with m being the mass of the drone and b being the damping constant. With this transfer function, we can model the open-loop drone system without any feedback. This demonstrates our input forces being summed, going through the transfer function and outputting the drone height. The plant was modeled with Simulink, using a mass of 1.5 kilograms as previously discussed, and a damping constant of 1.4. This model outputs the following result for height over time. Visually, the plant is seen to be unstable, with height increasing infinitely. This can be proven by analyzing the poles of the function. When the denominator of the transfer function is isolated, it can be factored as shown, and the poles that result in the denominator being 0 are s is equal to 0 and negative b over m. The open loop plant is currently unstable because of the pole at 0 and cannot be made stable without closing the loop. Because it is open loop, we have a bounded input but not a bounded output. Currently, there is a pole at 0 which indicates a system of type 1 if the loop was closed, implying it will be able to track step inputs perfectly and ramp inputs with some error, but it will not be able to track parabolic inputs. The speed of the response correlates to the size of the second pole, negative b over m. For our purposes, the plant currently has sufficient ramp speeds, being able to reach a height of 14 meters in about 20 seconds. The plant can and likely will be affected by outside sources. Wind speed and gusts are variables that affect drones. Wind gusts push off of the trajectory and resist motion. Because the drone is operating in the real world, conditions can be very unpredictable. Birds like to take an interest in drones, even making contact on occasion. These disturbances in the payload would affect the center of gravity of the drone and would affect how it reacts.
For our design, we chose to use a PID control in order to stabilize the system and improve the following metrics: steady state error, disturbance rejection, and settling time. Steady state error and disturbance rejection both come from steady state specifications, where settling time comes from transient response specifications. Steady state error is important because the pizza must be delivered and released at the correct location and height. A large error in terms of location would potentially leave the pizza in a location that is inaccessible to the customer. This same error in terms of altitude would potentially release the pizza at the wrong height, having the drone crash into the ground or have the pizza fall too far. Disturbance rejection is important because the drone will experience disturbances in flight like wind gusts, bird strikes, and changes to its center of mass after it drops off the pizza. Settling time is important because too short of a settling time could cause the pizza to get shaken around inside the box as the drone quickly tries to settle to the desired value. A large settling time decreases the drone's ability to quickly and effectively react to its surroundings. The PID controller is important because we want a fast response and response control, smooth tracking and steady state error, and disturbance rejection, and stability.
Through experimentation, the team found a PID controller transfer function that achieves our objectives. By multiplying the controller transfer function out, we can obtain the gains of the system. For our plant, the proportional gain was 16.875, the integral gain was 0.9, and the derivative gain was 12.15.
The Simulink model with the final PID controller and correct transfer function outputs a step response graph that meets our project specifications. One of the specifications was that settling time needed to be between 5 and 45 seconds. After analyzing the graph, the settling time was found to be 35 seconds. The other specification that needed to be met was the steady state error. We wanted this to be less than 0.6. Our steady state error ended up being 0.007 meters, which was found by doing calculations in MATLAB. Our final specification was that our system must have good disturbance rejection. It was simulated in Simulink using a step function as a disturbance. The graph outputted showed good disturbance rejection. The Nyquist and Bode plots of the system were also found and analyzed. The analyzation of the Nyquist plot showed a stable system as it never circled -1 and there were no unstable poles.
Having no unstable poles is in reference to the function L sub s, which is related to the entire transfer function of the system times the feedback transfer function, which is 1 in this case for unity feedback.
Thus allowing the equation z equals n plus p to be equal to 0. The Bode plots allowed for the calculation of the gain and phase margin. The gain margin ended up being infinite, which means that no matter what gain was added to the system, the loop would never go unstable. The phase margin ended up being 76.6 degrees, which then allowed for the calculation of the time delay. The time delay was 1.36 seconds, which means that the system could tolerate a delay of 1.36 seconds before the loop became unstable.
Overall, we were able to successfully meet our design goals for this project and are satisfied with our work. We think that by using our PID controller for our drone system, we would be able to more effectively control its vertical movement, leading to better pizza delivery. This has been proven by showing that our system is stable, has a reasonable settling time, good disturbance rejection, and good steady-state error tracking.